which is a fairly straightforward one. What I have is a very simple merry-go-round. So I have a carousel, and there's the load, there's the person, there's this horse or whatever it is, and the person is sitting on that, right? And it's going round and round this way with a speed of 10 rotations per minute, right? Let's say the length of this thing is about 4 meters. The question is, how much will it swing out? What is this angle? Right? So we're going to find this out. So notice it's going at a constant speed, 10 rpm. So first step, draw free body diagram. And in our case, that's the free body diagram of this person. Like that, they're sitting there. Of course, looks like a spider, but I'm sorry about that. So there's this bar which is pulling, T. There's the gravity, mg. Right? And we know that this angle is theta. That's it. That's the free body diagram. So let's be very clear. Centripetal or centrifugal forces or band. I just want you to say there are only two forces. This is not balanced. Who says forces have to be balanced when things are moving? They are not balanced. Now this must be equal to the acceleration vector on this person, mass times the acceleration vector on this person. So for that, you first have to say, do I know the path? The answer is yes. It's going around in a circle. So let me write down, path is a horizontal circle. So now, how much is the acceleration along the path? The acceleration along the path equal to 0. There is no acceleration along the path because constant speed, rate of change of speed, that's 0. Acceleration perpendicular to path equals speed squared divided by radius of turn right, pointing concave side. So let's see which way is the concave side. The path is like that, so the concave side is like that. Can you see that? So that's the direction, and this will be mass times speed squared divided by radius of turn. So now we have the equations that we need. This is the only acceleration component. So this vector system must be equal to this vector system. That's all we have to do. Okay, so let's do this. The way it's going to work is the following. So here was the tension mg equals m speed squared divided by radius. So if you look at the carousel looked like this, right? The radius of the turn is that r, which is a, this length is 4 meters, so this angle is theta. So r equal to a plus 4 meters cos sine theta. That's the radius of the turn. Speed equals 10 revolutions per minute times 1 minute for every 60 seconds times 2 pi radians per revolution right? So you can say revolution got cancelled out, minutes got cancelled out, and then times radius in meters, right? Which turns out to be 2 pi times 10 over 60. So 2 pi over 60 times radius times r meters per second. So now we are ready. This angle is theta. So you will get summation of all the forces, vertical positive will give me T cos theta minus mg equal to 0, because there is no acceleration this way. Summation of all the forces this way gives me T sin theta equal to m speed squared, which is 2 pi r squared divided by 60 squared, sorry, divided by 6, 10, 2 pi r divided by 6 squared divided by r, right? And you can substitute for r from here and you will get T cos theta. So T cos theta equal to mg and T sin theta equal to this, T cos theta equal to mg, T sin theta equal to 4 pi squared mr divided by 36. Right? So divide the two things and you will get tan theta equal to, you will get some nasty thing, that's life, you know. Tan theta equal to m gets cancelled out, 4 pi squared r over 36g, and r itself has sin theta in it, so you have to solve for sin theta and cos theta. That's how it works. Okay, what I want you to understand is that we can actually find the angle systematically. The only difference between what we did in statics and what we did in dynamics is the fact that the right hand side is now not 0. It is obtained from the kinetic diagram, acceleration diagram. Okay, so example 1 is done. Let's look at example 2 now. In this case we have a very simple thing. Here is a freeway, here is an off ramp from a freeway, and the radius of this off ramp is r, and a motorbike is going on the off ramp at constant speed. Okay, what? So when that happens, the question for us is, I'm going to look at it from front view. So I cut it like this. Here is the center of this off ramp. Here is the off ramp. Here is the motorbike. Here's the person. Here's the handlebar. Here's the person standing like that. You see what I mean? The question is, what is this angle theta? And you know the motorbike has to tilt in the direction of the rotation, right? Otherwise it's not going to go. The question is, what is this angle? So how do we do this? First we ask ourselves, what are the forces on this person? For this you have to say, okay, here is a motorbike. Okay, so the center of mass of the motorbike is here with the person, and there is the weight of the person, gravity. The road is pushing on it, N, and you need, in order to take a turn, you need friction. Without friction you cannot turn. So what is going to happen with friction? The answer to that comes from, you have to figure out what will happen if there is no friction, because remember, friction opposes sliding. So what happens as soon as there is no friction? As soon as there is no friction, is it obvious to you that this tire will fling out and this guy is going to fall down like that? So what happens is friction will oppose this. So friction force is going to be like that. These are the forces on the motorbike. Now let us look at the acceleration side. So now is it obvious to you that the path is known? Right? So that's why we are using path coordinates. There is the path given. So that's the first question to answer. The second question to answer is which is the tangent direction? That's that way. That's coming out of the board. That's the tangent direction. The normal direction is going to be on the concave side of the path, which is that way. So the normal direction is that way, En. Right? Et is pointing towards me, En is sideways. So what is the tangential acceleration? Is ddt of speed, that is 0. Normal acceleration is speed squared over radius of turn. That's going to be there. So our kinetic diagram will look like this. Mass times speed squared divided by radius. Okay, so this must be equal to that. Okay, so let's see if you can solve this thing. So on the left hand side we had weight, normal, friction, and this angle is theta. On the right hand side we had just this thing, which is mass times speed squared divided by radius. So it's pretty easy. We are just going to sum all the forces in the vertical direction. Positive equal to 0 gives me W equals N, because W, let me write it down, minus N plus W from this side equals 0. There is nothing here on that side. Summation of all the forces, sorry, mass times acceleration. So summation of all the forces this way positive equal to mass times acceleration this way gives me F equals mv squared over r. Can you see? First thing I want you to notice is friction is necessary for it to take the curve. Okay, but you can see that unfortunately for us, W is known, this is unknown, that's unknown, radius is known, v squared is known. We can calculate the friction force. If the friction force happens to be less than mu times normal,